Good afternoon. We're going to start our final series of 3 keynote talks. And the first speaker will be Mary Hill, who will be talking about testing modeling frameworks.
Thank you. I'm really enthusiastic to be here. This is, has become one of my very favorite meetings, so it's great to be here. Okay, so my subtitle that I added is, I guess I can look at this. Let's see. How can we improve predictive skill from our data? So we collect all this data, we put all this time into developing our models, and how can we use them together better? Okay. I want to acknowledge my co-authors, Laura Folia, currently at Technical University of Darmstadt, soon to be at UC Davis, Ming-Ye at Florida State, Lu Dan at Oak Ridge National Lab. Okay, so when we look at frameworks for model analysis, what I'm talking about, are, when I say frameworks, it's frameworks for model analysis. And what we're looking for really is surprises. There are things we assume about our models that we think we know about our models and understand. And the reason we go into more analysis is to sort of question, are we right about that assumption? Are we right that that's the important data? Are we right that that's the important parameters? And surprises can indicate new understanding about reality or model limitations or problems. A consistent theme through much of my work, actually, and certainly this talk, is that it's really nice if we can conduct these kinds of analyses quickly, because that enables routine evaluation. And so we're going to look for what I'm going to call computationally frugal. That means it doesn't take a lot of model runs, and parallelizable methods. I won't say too much about that, but I'll mention it a little bit. Okay, so what do I mean by modeling framework? What's involved in that? It includes things like parameterized system characteristics, how we compare our models to data, how we adjust our models, often parameter values, but sometimes other things, to match the data, and what does that mean? Doing sensitivity analysis and doing uncertainty quantification. Okay, I'm going to comment on a couple of these. I'm going to make this part of the talk a little shorter than I had originally envisioned because I think I'm going to be over, so I'm going to skip a couple of these. But this one I'm going to go into. One of the things we look at in a framework is how are we going to parameterize the model. I work in groundwater models, so primarily, so that a lot of what I worry about is how am I going to represent a 3-dimensional spatial quantity, which for me is hydraulic conductivity. And these are kind of the endpoints of how ideas about how this can be done. One is geologically based, where I define zones or simple interpolations and estimate a relatively few number of parameters because I'm using the geology to constrain the spatial distributions that I'm going to consider. The other one that's the other endpoint is to define many interpolation points. Every one of the small crosses on that figure is a place where a parameter value is estimated, and then those are estimated based on both prior information about the values and the values at each point. And there's work that's been done for both these kinds of systems on how accurate they can tend to be. And I'm going to talk about an example that used the one on the left. We can also look at comparing data. We've seen some really nice graphs comparing simulated and measured data, simulated and data and measurements, simulated values and measurements. We can also look at statistics like sum-squared rated residuals or sum-squared residuals. I'm going to skip this one for now. We can also do sensitivity analysis. The points here are showing a comparison between simulated and observed values, okay? But we're also showing here a statistic that measures how important that data is to the model fit, in this case, the estimated parameters. So essentially, which of all those data points is actually contributing much to the to developing the model, in this case, as I said, to estimating the parameters. There's other sensitivity analysis you can do to say which of these data points is contributing to predictions. But that means that you're not just looking at the fit to data, you're looking at how important those points are. Okay, and then there's uncertainty quantification. I'm going to skip over that for now. Okay, basically for these framework methods, for these frameworks, these modeling frameworks, there's a lot of methods. And there's an article that I wrote with some others recently that we published in Groundwater that talks about how many methods there are, kind of the Tower of Babel and how it can be confusing to people, and also that some of these methods, which are in the right-hand column here, require really demanding computational resources, like 1 million model runs. And when you have to do that just to do a model analysis, it's then very hard to go deeper into the problem. And that the other point here is that you can use frugal methods for basically any step of the way. Any step you have a choice between computationally frugal and computationally demanding methods. Okay, so I'm going to talk about one particular example of testing modeling frameworks and how some of these methods can be brought in to do that. And the case that I'm going to look at is the Maggia Valley in Switzerland. The goal of this study was to develop an integrated hydrologic model to help manage the ecology of this altered hydrologic system. The system's been altered, as shown in the bottom right, by installation of upstream dams in the mid-50s, and which left high flows fairly unchanged, but dramatically changed the low flows to be much lower than they had been before, and that has been affecting the vegetation in areas like that on the right, which is a national park. Okay, I'm going to present results from one of a series of studies we've done here that built on one another. The problem is that integrated hydrologic model, that's the goal of this ecological study, takes a long time to run. We're going to use the component surface water and groundwater models to test methods to see if we can find frugal methods, computationally frugal methods that we can use on that computationally demanding integrated model. Okay, so the series of studies started with a 2007 publication where we compared where we looked at sensitivity methods. Then we looked at demonstrated calibration methods that were computationally frugal. In this study, we're taking the results of those two, and we were using it to test computationally frugal model selection criteria. I'm actually going to show you a different part of the study than the model selection criteria comparison. And then I'm also going to show you one result from something that's still ongoing, where we actually finally got to the integrated hydrologic model. And the software we used was UCode and multimodal analysis. Okay, so this is the site, and showing on the left the flow data in triangles. So the stream flows are measured there during presumably base flow circumstances. We take differences between adjoining flows to get stream flow gains and losses, and that's our data. On the right is the valley with the head data shown. So, excuse me, there's about 28 head data points. Okay. And let me show you this one first. In the cross-validation exercise, what we did is take out some of the data points, calibrate with the rest of the data, and looked to see what the characteristics were of models that could reproduce the data we had omitted best. Okay, so that's how we're testing our mechanisms for developing this model. Okay. For this cross-validation, we considered a bunch of different models. They varied in terms of how the stream flow was represented. There were two options used. One, these were options in ModFlow, which was used to simulate this system. And if you look at this figure, this is the stream flow routing package, which allows water to be routed down the river. Okay? Because it allows routing, it only allows you to use a single kind of set of points to represent the river. But in this case, the grid is 25 meters on a side, and parts of the river are fairly wide. So the river is actually wider than the grid spacing. So there's another package called the RIV package, which allows us to represent the entire width of the river, okay, but doesn't allow us to route water. Okay, so those are those two differences. There are also differences in how we handled the recharge. It was either 0, a constant, which was could be estimated as a parameter, or a full rainfall runoff model that was used to calculate a spatial distribution of seepage, and then there was a parameter to just multiply that. The bottom bedrock could be defined in two ways. One was before a gravimetric survey was done and one after. And the difference in that was a factor of 2 in the bedrock, the thickness of the valley fill deposits in the south. For hydraulic conductivity, we had a quaternary geologic map, which is shown on the right, and that was used to, and it was only available in the northern part of the area, but we used it to divide the area up into zones. In this case, with a fairly narrow range of hydraulic conductivity, just about 1.5 order, well, within about an order of magnitude or so. The hydraulic conductivity distributions, we worked with homogeneous as one option, and then there were 5 combinations that varied from that one parameter as being homogeneous to 6, and that ends up with 64 alternative models. One of the things, if you think about those points that we're taking out, if we took out, and we selected a group in the middle of the system because that's where there was most interest in the quality of the predictions. If all those points we took out didn't matter, if they were all low sensitivity points, if they weren't influential at all, that's not a very good test. It's also not a very good test if they're all the important ones, okay, and all the rest of them are not important. So we can do an analysis, which we did here. This is a statistic called leverage, which we can use to identify which observations are important and not important. And this is one of the statistics I used on that previous figure too. So the gray shaded areas are the ones that we are taking out. And you can see that there's a combination of things with high leverage and low leverage compared to the rest of the data set, suggesting that this is actually a good set of observations to have taken out from this sensitivity perspective. Okay. Okay, the test conducted, as I said, there's the primary purpose really of the article was to test model selection criteria. And we found problems with doing that, especially with what I'm calling the KIC criteria. What I decided to present here are some other results in which we compared the results to a basic premise about model development. Okay, the basic premise is that if you increase the complexity of your model, in this case, I'm suggesting that's done by adding parameters, but you could do it by adding processes, okay? For any given set of data, so your set of data is the same, it's kind of like your ruler that you're using to evaluate your model. That model fit, which is shown in blue, will always tend to get better as your number of parameters increases or as your model complexity increases. But your model prediction capability will get better, but then it'll actually get worse, because what's happening is you're fitting your data at this point. You aren't really representing real processes. So just getting a good fit isn't going to guarantee you to get the best model, okay, the best predictive capability. Okay, so we can take, this is the basic premise, and that's been around for a long time. But it's very rare that you actually have studies compare against it, okay? So in our case, we had the data to do that from all these different models. We had models that differed not only in a number of parameters, but in how those parameters were used and what processes were developed. So we don't get one single nice curve like this, okay? But if we do plot the sum of squared weighted residuals, our measure of model fit, with respect to the estimated parameters, we do get a curve, and actually we get a function that for any given set of other conditions besides hydraulic conductivity, we're seeing that the results are really pretty flat, okay, except for that point, okay? And then if we go from top to bottom here, the ones that are filled are the ones with the streamflow routing package, and the ones that are open are the ones with the river package. So we see that the river package in calibration phase is actually doing that a little better. Okay, and the fact that these are so flat when really we don't have that many parameters is suggesting that the lack of improvement with added hydraulic conductivity parameters indicates that the hydraulic conductivity parameterization based on that geologic reasoning has little relation to the processes, because if it did, this should be getting better. So, okay, one thing we've determined, and this is actually a kind of result that you could do in any problem. We don't have any advantage here from the cross-validation experiment per se. This is a way you could evaluate an aspect of the model and whether or not it's getting better, and whether it's really contributing. Okay, the other aspect of this figure is the predictions, and in this case, when we did cross-validation, we have prediction results. Okay, so here what's happened is adding those parameters, especially the hydraulic conductivity parameters, didn't change model fit much, and you might have thought, well, it doesn't really matter, I'll just stick them in, okay? But the predictions get much, much worse, okay? And why would that be? The problem is that the sensitivity is that when you add those parameters, you're off into a parameter space where things are really correlated and really the sensitivities are really flat. So your data isn't informing those parameters at all, so they can wander off of what would be realistic. And the sensitivity analysis shows this. We can identify it beforehand. You would not be able to construct a figure like this with prediction error without doing a full cross-validation, but you could at least have a figure like this where you showed how your prediction changes as you add parameters. You could add something about the sensitivity analysis to help you see if you're in a position where you're really poorly posed, and that could indicate how accurate your model is. And so it's an integration of this analysis of sensitivity, analysis of model fit, to help you understand how much you're informing your solution with the data you have. What do poor predictions look like? In this case, this is for hydraulic heads, and this is the observed minus predicted value for heads. Here's the 0 line. And you can see that these really bad solutions just get really poor heads, particularly in the extremes of the case. Okay. Okay, and I'm a little short on time, so I'm going to go over this really quickly. Actually, I'm going to skip this part, so I'll just go to my conclusions. So the conclusions for this test is that the superficial geologic mapping did not provide a useful way to parameterize the hydraulic conductivity. The sensitivity analysis could be used to determine when the model detail exceeds what can be supported by the data. Models unsupported by the data were likely to have poor predictive capability. And in the article, there's, from this and the rest of the analysis, there's 5 specific suggestions for model development. Okay. One thing in doing this test, and as is common, this was enabled by computationally frugal model analysis methods, which are enabled by computationally robust methods. And this is where you, the model developers, come in, okay? Do your models have numerical demons? Okay. Okay. What I'm showing here is a figure that comes out of Kvetska and Kucera, a 2007 WR article that was spruced up and published in a recent article that I worked on with Dmitry Kvetsky. What's shown here are ways to represent melting. Okay. And melting, indeed, there's no melting. Then this is temperature on this axis, and this is melting here. If the temperature is cold enough, you don't get any melting. And as you get warmer, eventually you get to where you start melting, and it increases, okay? And maybe linearly, okay? And if you have a relationship like this with a very distinct break in slope there, you get an objective function, okay, that looks like this. Okay, what's an objective function? This is temperature on this side, This is the slope of this line, the melting rate on this axis. And they calculated melting that occurred and had a set of values that they used as observations, and then took the difference between those, where they would get simulated melting using some temperature and some melting rate, and look at the difference between the melting that occurred there and what was observed, and they'd get 1 point on this figure. Okay? And they did that for lots of different temperatures and lots of different melting rates, and you can plot that all up, and you can see in this figure that it's very rough and irregular. Okay? This figure, to find this minimum, tends to take something like 1,000 model runs. Okay? It can take quite a while, quite a bit of effort to do this. Okay, in this figure, we still have the basic nonlinear relationship that's important to melting, but we've just smoothed it out. They smoothed it out a little bit right there. Okay, which in natural systems where you have a piece of ground and that you're representing in your model, and there are different parts of it. It's rough, maybe it has different aspect ratios. It probably makes more sense that this isn't a distinct point, that it's actually a smooth curve. So we've made it more realistic, probably. Okay, and the objective function here becomes smooth. And I can get to that minimum point in about 10 model runs, okay, many of which are parallelizable. Okay, so this is something that's easy to analyze, and this is something that's hard, and I've made my model more realistic. Okay, okay, so the important nonlinearities, such as that when things are frozen, nothing melts, and when they're warmer, they start to melt, are important. Keep them. You have to keep them. But get rid of these unrealistic nonlinearities. And every model has these. Okay, and usually when I talk to people, they'll say, you know, oh yeah, I have this one. In ModFlow, we have them. Okay. This is a figure that I skipped over before, and I'll just say it quickly, just point it out quickly. These are the parameters of the integrated hydrologic model that was produced for the Maggia Valley. And this is a measure of parameter importance. And so we can see which parameters are important. In this case, there's some soil depth parameters, there's the porosity. These are from the surface water model, these are from the groundwater model, which the models have been integrated in a way that makes it so the surface water data doesn't affect the groundwater. And then for each of these points, we can also say what kind of data contributes to that parameter being important. You can only get these kind of results quickly and on the fly and conveniently if you get rid of your numerical demon. So this is the prize that you get in the end. Okay, so and I have just a little perspective. In 100 years, we may very well think, very well be thought of as being at the Model T stage of model development compared to automotive. You know, if we make an automotive analogy. A prediction is perhaps that in the future, simply getting a close model fit won't be enough. Maybe even now it's not quite enough. It will also be necessary to show what observations, parameters, and processes are important to that good model fit. When I sit in AGU and look at people's results and they just say, I got a good model fit, I'm like, why? Is it just because you had precipitation? You know, the distribution? Did anything else you do matter? Anyway, and this increased transparency is like the safety equipment on the automotive development. I'm looking for test cases to test these kinds of methods out. I have ideas for how to detect numerical demons, and I'd love to work with some of you on that. Also wanted to say that AGU has a new technical committee on hydrologic uncertainty. SIAM has a new SIAM uncertainty quantification section and a journal, so there's a lot of motion in these fields. And that's what I had to say. Thank you so much.
I was wondering your frugal methods for estimating uncertainty and kind of parameter evaluating. I wonder how that compares to maybe a more extensive analysis, something like pest or something like that, especially for the groundwater.
Yeah,
components?
I'm not sure which PEST so PEST has two capabilities. One is is the frugal methods, the local methods, and one's called a he calls it the prediction analyzer, okay, which is a nonlinear confidence interval. And I actually have results from that, which I skipped. Oh, I may have taken. Just a second, going too fast. Okay, so that's what I wanted to show. I didn't. Okay, let me. It would be helpful in answering your question, so let me try to get to it without blasting by it. Okay, so the ones in PEST are the linear confidence intervals and the nonlinear confidence intervals, okay? And this is for a groundwater problem. And so, I can describe to you the theory behind the nonlinear confidence intervals if you want to, but anyway. And the other alternative that's been very popular recently are Markov chain Monte Carlo intervals, and those are the ones in the green. Okay, in this particular problem, and this is a problem in which we're considering alternative models, and for each of those models, we're calculating these three different kinds of confidence intervals. Okay, and what you can see here, the conclusion from this paper, which is Liu et al. 2012, is that the extra effort to calculate the confidence intervals isn't as important as putting in the effort to consider alternative models. Okay, so that's all of these confidence intervals are these three kinds of confidence intervals are calculated in our new version of UCode 2014. And it's not in PEST, but there's I can't remember the name of it, but there is an alternative, like a companion code to PEST that does what are called nonlinear credible intervals here, which are the Markov chain Monte Carlo. We had trouble with that program when we did our work for the Liu et al. 2012. You could look at that article if you wanted to see what difficulties we had, or I can talk to you. So, good. Thank you.